This is another horizontal projectile motion, 1590, some 400 years ago. Galileo, an Italian scientist, a professor of Pisa, 1590, 26-year-old Galileo, a professor of mathematics at University of Pisa, famously hypothesized that projectile motion means that a rolling ball with some velocity, let's say 10 meters per second, all right, roll off the cliff, roll off the table, edge of the table with 10 meters per second, take exactly same amount of time to hit the ground if you drop the ball from the same height. Okay, so this problem will allow us to understand this hypothesis. Okay, so now let's draw a table. Table is 1 meter. Table is 1 meter tall because 1 is simple number, and I don't have calculator. So let's make it 1 meter. So a ball roll on the table, and we want to with velocity v. We're gonna find out what is the velocity v. So roll off a table, and eventually when it arrives at the edge of the table, it start falling. So it's eventually land. So this ball eventually land right here, of course. All right. So when we measure this one turned out to be I don't know. Say this is 1 meter. This is 1.2 meters. All right. Okay. Oh, this is 0.8 meters. 0.8 meters. It doesn't matter. All right. So now what do we know? We know almost everything because of Galileo. We know the velocity over here, right here, because velocity has two components. All right. So this is the velocity, Vx and Vy. I know Vy is 0, and I know Vx. I don't know V initial x. To be more precise, I want to write V initial x, and to be more precise, I want to write V initial y. All right. V initial y is 0. V initial x we don't know. We'll find out. It's so easy to find out. So what do we want to know? We want to know a lot of things. We want to know the initial velocity. We also want to know the time, hang time, how long the ball was in the air. So how can we find out how long the ball was in the air? D is equal to VIT plus half AT squared. All right, make sure this is at the y direction, Okay. All right. Good. So the dy is -1. So if I make this number 10, will that make our life easier? Yeah. So I'm going to make it 10 meters. So the table is 10 meters tall. Who cares? So VIY is 0, of course, plus half -10 t squared. All right. Let's make table 5 meters. 5 meters. Table is 5 meters long. So -5. All right. So -5 is equal to -5 t squared. Voila. I don't want to use the calculator. Not today. Negative cancel. So, and you divide both sides by 5, and then what do you get? So 1 is equal to what is it? T squared. All right. So then t is equal to square root of 1. So t is equal to 1. All right. So the hang time is the t right here. T right here is 1 second. All right. The ball was in the air for 1 second. Okay. That makes sense. Of course, that makes sense. All right, it has to make sense. I want to find the initial velocity. How can I find the initial velocity? It's so easy to find the initial velocity. Okay, so I don't want to use the calculator. So what number this should be so that I don't have to use the calculator? Maybe 2 is a good number. So 2 meters. So the ball falls, rolls off and falls 2 meters away from the edge of the table. As simple as that. Now, I want to find the initial velocity. How can I find the initial velocity? D is equal to VAT plus half AT squared. In this case, we use the y component. Now this time we're going to use the x component. Why x component? Because I want to find the x component of the velocity. To find the x component of the velocity, I have to find the x component. This is 0. Acceleration due to gravity at the x direction is 0. I cannot stress it enough. You better remember that. So the dx is 2 meters. All right, so 2 meters, and I'm just going to use right to vix. That's what we try to find, and t is of course 1. All right, so the vix is equal to 2 meters per second. All right, so initial velocity is 2 meters per second. All right, so now I'm going to show you some graph. Very important. So now this is dxt, this is dyt, this is vxt, this is vyt. All right, so dxt, what happened with this one? All right, now let's draw some. Let me give you some inspiration to do that. I'm gonna draw the velocity vector. To draw the velocity vector, I need a different color. All right, I'm gonna use the green for the x component, and the x component velocity is what that tells you. What does that tell you? This same size, this little longer, same size. So at the x direction, velocity is constant. At the x direction, velocity is constant. That's what it means. If velocity is constant, then the displacement must be, if this one is the horizontal, then this must be diagonal. As simple as that. Now I'm gonna change a little bit over here. The y direction, everything have happening over direction because ax is 0. Yeah, that's why this is not that interesting. What makes this one interesting is ay is -10. So this is dyt, and this would be vyt. All right, now what do we know about vy? Let's draw it. All right, let's draw the velocity. So here is 0. Here velocity y direction is 0. Here is small. Here is little bigger, and here is much bigger. So what's going on? It starts from 0. I can even calculate the final velocity. Let's calculate the final velocity. Total time is 1. The final velocity v final is equal to v initial plus at. Remember, this is y direction. Everything is happening y direction. vfy is equal to vi. Y is 0, so -10, and then this is 1. So -10. So this is -10. All right, and this is 1. So now this is the point. All right. Okay, so this is the graph. I can make it red, so making it more standing out. Now dyt. Now if this is a diagonal line, this must be a quadratic. And also I know why it is quadratic. If you look at the distance, then you see it is quadratic. The first second and the second second and the third second, first second falls -5, and the second second it falls -20, third second it falls -45, and fourth second falls -80. So so it must be quadratic. So all right, so now next one. So this allows us to understand what 400 years ago Galileo 1590 at University of Pisa, Italy, said that object horizontal projectile motion, object rolling on a table with some velocity takes exactly the same amount of time to hit the ground as you drop the object.